The splitting field of an irreducible polynomial is the smallest subfield of the algebraic closure of its coefficients that contains all of the roots of that polynomial. Because of that, it's easy to understand why the splitting field of a given polynomial carries all of the information that we will ever need about the roots, the nature, the number, and the relationship between the roots of that polynomial. So it stands to reason that in order to understand the roots of a polynomial, we should really understand as much as we can about the structure of that polynomial's splitting field. In this video, I'll introduce you to a powerful tool for understanding the structure of a field extension, and those are the automorphisms of that extension. We'll look at how the automorphisms of an extension are similar to the symmetries of a geometric object, and using that comparison, we'll look at how to determine the automorphism group of a couple of field extensions. So the question is, in order to understand the splitting field, or really in general any field extension, we want to understand what are its symmetries. Because the idea is if we can understand enough information about the symmetries of an object, then we know that object's essential properties. In other words, we can understand, for example, the splitting field of a polynomial if we understand what are all of the ways in which the symmetries can act on that splitting field. So here's some deep background coming from geometry, because this is hopefully something that's reasonably familiar. If I have a polygon, let's say a rectangle, then one of the standard beginning geometry exercises is to think about what are the symmetries of this polygon. What linear transformations can we apply to this rectangle such that the rectangle that we get in its image is exactly in the same spot as the original? Well, we have a horizontal axis of symmetry that we can reflect across. Let's call that reflection something. Let's call it A. So A is reflection of this rectangle about its horizontal axis. Likewise, we have a vertical axis of reflection as well that's different from A. Let's call it B. And if we take A and B and we do both of them, we get another reflection that first takes us horizontally across the vertical axis and then vertically across the horizontal axis. And so the net effect, really, is a rotation of this polygon by 180 degrees. So those three symmetries of this polygon, combined with the most boring symmetry in the world, the identity, in which we do nothing, form a complete description of all of the symmetries of this rectangle. How about an equilateral triangle? Well, an equilateral triangle also has a reflection about a vertical axis, for example. Let's call that T. And then we also, for an equilateral triangle, get this 120-degree rotation. Let's call it R. But then we can do that rotation twice and get a 240-degree rotation. Let's call that R squared. And we can combine T's with R's to get something like TR, which turns out to be a reflection across this axis, and TR squared, which turns out to be a reflection about another axis. So what we end up with are sort of three reflections and two non-trivial rotations, taken together with the boring identity, give us 6 different symmetries of this equilateral triangle. Okay, great. So that was the original exercise from beginning geometry. How can we doll this up a little bit with the tools of abstract algebra? Well, the first thing we want to think about for each of these symmetries are what is that symmetry's invariance? In other words, when I apply a symmetry operation, what stays put? For example, if I apply the identity symmetry to the rectangle, the whole rectangle stays put. And so we would say that the invariant of the identity acting on this rectangle is the whole rectangle itself. For the reflections, it's a different story. If I apply a reflection about the horizontal axis, then all the points on that horizontal axis are going to stay put. So we call the horizontal axis the invariant of the symmetry A. Likewise, for a reflection about the vertical axis, we get the vertical axis to be the invariant of that transformation. And then the 180-degree rotation is kind of interesting, because only the point that's in the center of this rectangle will stay put. So only that point is an invariant of that symmetry operation. For the equilateral triangle, it's a similar story. The identity fixes the whole triangle, the reflections each fix their respective axis of reflections, and the rotations each only fix that point that's at the center, the barycenter in this case, of the equilateral triangle. Now the great thing about this is that symmetries, when we compose them together, also give us symmetries. And so the set of all of our symmetries, taken together with the operation of composition, will form a group. We call it the group of symmetries of this polygon. So for the rectangle, if I replace AB with C, so we can just write it down a little more simply, then we can construct a multiplication table, a Cayley table, for all these operations. And once we've done that, we can understand what the structure of this group of symmetries ends up being. But actually, we want to look at this yet another way. If I take the vertices of this rectangle and I number them, there are only 4 of them, 1, 2, 3, and 4. And every symmetry operation is going to take one vertex and carry it into another vertex. After all, when we apply a symmetry to this rectangle, the new rectangle has to be in the same spot as the old one was. And so a vertex has to be where another vertex used to be. So for example, the identity transformation is going to leave all of these 4 vertices in place. So it's going to be the permutation of 1, 2, 3, 4 that sends it to itself, 1, 2, 3, 4. That's the identity permutation. Meanwhile, the reflection about this horizontal axis is going to flip-flop the 1 and 3 and the 2 and 4. The reflection about the vertical axis is going to flip-flop the 1 with the 2 and the 3 with the 4. So each of those can be represented by an element of the symmetric group on 4 symbols. Each case, they happen to be 2 plus 2 cycles. And then with our 180-degree rotation, we end up flip-flopping 1 with 4 and 2 with 3, at least the way that we've labeled the vertices on our rectangle at the left. And so what we've done here is we've realized this group of symmetries actually as a subgroup of the symmetric group on 4 symbols. And there's a key observation, is that if I'm looking at the symmetries of an n-gon, so a polynomial with a polygon with n vertices, then that group is going to be isomorphic to a subgroup of Sn, the symmetric group on n symbols, where the symbols here correspond to the vertices of that polygon. And for this particular example, we find out either by the Cayley table or by looking at the 2 plus 2 cycles that make up the subgroup of S4, that this symmetry group is really isomorphic to V, the Klein 4 group. For the equilateral triangle, if we list all of those elements of the symmetric group which correspond to these symmetries, again numbering the vertices, like 1, 2, 3 for example, we find out that the identity, again, doesn't move any of my vertices. The reflection about the vertical axis flip-flops what I labeled 2 and 3. The 120-degree rotation corresponds to the 3 cycle, 1, 2, 3, because 1 goes to 2, 2 goes to 3, and 3 goes to 1. The 240-degree rotation to 1, 3, 2. The TR reflection is 1, 3, and the TR squared reflection is 1, 2. And all 6 of these operations are different. So that subgroup of S3, to which the symmetry group of this triangle is isomorphic, will have 6 elements. But since S3 itself has 6 elements, that must mean that this symmetry group itself is isomorphic to S3, the full symmetric group on 3 symbols. So this is the beginning of the story. And one of the observations in the history of mathematics that has really been revolutionizing the way that geometry people think about geometry is something that in the 20th century was called the Erlangen program. And in the Erlangen program, the idea is as follows. The Erlangen program says that we can build a geometry, for whatever that means. Let's think of it as we can understand all of the essential properties of a geometric object only by understanding the stuff that's in the 2 columns on the right here, with only the information that we have about the symmetry group and the invariance of the elements in that symmetry group. In other words, if I know all of the information on the right side of this page, then the Erlangen program says I should be able to reconstruct the information on the left side of the page. Now, there are a lot of different polygons that might have Klein 4 symmetry, for example, an ellipse or maybe some non-convex polygons. But the idea is that all of the geometries of those polygons would be equivalent in some way. So understanding the symmetries of an object should help us to understand and then possibly to recreate that object, if we also know what the invariance of those symmetry operations are. So in the next video, we want to run with this analogy a little bit more and think about how an extension of fields might be similar to one of these polygons, and how we can define a notion of symmetry for field extensions that will help us to understand what is the symmetry group of those field extensions, and then hopefully thereby understand the structure of those extended fields.